Okay, welcome. So I'm Stoica. I am a faculty in computer science, and I am one of the co-directors of the AMP Lab. I'm going to talk a little bit more about that. And today, I'm going to give an overview of the Berkeley Data Analytics Stack, which is a software stack, open source software stack we are building here, which we hope to be widely used both in academia and industry. So first, let me motivate it, although I don't think it needs any motivation why you do this for this audience. But anyway, so what do people use big data for today? Well, first they use it to generate reports, to track and better understand business processes, transactions, and so forth. Second, they use it to diagnose and answer questions such as why is the user engagement dropping, why is the system slow, or maybe detect spam, worms, viruses, or denial of service attacks. But most importantly, they use the data to make decisions, such as personalized medical treatment, decide what feature to add to a new product, or the canonical examples of our time, decide what ad to show to a particular customer. So really our research and what we do is driven by the belief that data is only as useful as the decision it enables. Then what are the data processing goals? Well, you want low latency to support low latency interactive queries on historical data, because the faster you make a decision, in general, the better. You want low latency not only on historical data, but also on live data, because many times decision you made on the fresh data is better than the decision you made on a stale data. And finally, you want sophisticated data processing, because many of the decisions are not like just SQL queries. For instance, anomaly detection, trend analysis, they are based on sophisticated machine learning, graph-based algorithms. So you want to support those. So now today, Open Analytics Stack, and when I am saying today's Open Analytics Stack, I'm referring mainly to Hadoop ecosystem. Hadoop Stack is mostly focused on large disk data sets, and they are doing a very good job on that. So you can run sophisticated algorithms, but there are batch algorithms on these systems. And just to put things into perspective, this is how we look at this stack. It has 4 layers. The bottom layer is the infrastructure layer. So fundamentally here it is a cluster on which you run the software. You have a storage layer, which typically is a distributed file system, like Hadoop distributed file system. Then it's a data processing layer. And here you have a bunch of frameworks, cluster computing frameworks, such as Hadoop, HBase, MPI, Hive, Pig, and so forth. And finally, you have applications, right? Data analysis, data mining, decision-driven application, and so forth. So now, what are our goals? Well, our goals are the following. First, we want to support all the basic computation processing models. We want to support batch processing, interactive processing, and stream processing. And we want to do that in only one stack. Not only we want to support batch, interactive, and streaming processing, but we want to allow the user to easily combine these models. You can write applications which combine all these models. For instance, if you want anomaly detection to implement an anomaly detection application, then you are going to want to do maybe in real time, so you need to have streaming capabilities, but then you want to see whether, if you have now there is a peak. Maybe you want to look at last day, the same time, to see whether this is diurnal pattern or maybe something out of ordinary is indeed an anomaly. So you need the capability to fast query the data from the past to decide whether it's an anomaly or not. And then as the data arrives, in order to make it easily queryable, you probably want to pre-process it, pre-compute some results. That's batch. We also want to make it easy to develop sophisticated algorithms. And finally, we want to be as much as possible compatible with the existing open source ecosystem, Hadoop and HDFS. So what is our approach to achieve these goals? In order to support interactive and streaming computation, we are aggressively using the memory. And why? Well, that should be obvious. This is a high-end node in a data center today. So it has maybe 16, 24 cores. It has maybe 10 or more disk drives between 1 and 3 terabytes. So you have 10, 30 terabytes. And maybe you have some SSDs as well, say 1 or 4 terabytes of SSDs. And then all these nodes, you have also 120 or 512 gigabytes of RAM, and it's typically connected today with a 10 gigabits per second link to the other nodes in the cluster. Now, if you look at the I/O between the CPU, where the processing happens, and different components, you see that even for 10 disks, the aggregate throughput is only between 0.2 and 1 gigabyte per second. SSDs are a little bit better. Here you have between 1 and 4 gigabits per second, but here you have only 4 disks. And for memory, you have much more, between 40 and 60 gigabytes per second. So memory transfer rates are clearly much higher than the disk or even SSDs. And this graph is growing, especially with respect to disk. Right? So memory is much faster. Everyone knows that. This is to give you some quantitative numbers to put things into perspective. The second thing, it turns out that when you look at these data analytic, the clusters in industry, which perform data analytics, like in the case of Facebook, Yahoo, and Bing cluster, it turns out that, yes, there are some very large jobs, which takes a lot of resources. However, the vast majority of jobs are pretty small. The aggregate inputs of 90% of the jobs in all these cases fit in the memory of the cluster, in the aggregate memory of the cluster. Why? Because these are the results of kind of explorative queries. And you don't look at the entire data, maybe you look at 1 hour of data or 1 day of data, and you ask multiple questions about it. Putting it another way, it's another argument that the memory increases, and today, 1 terabyte, just a few nodes. You have 1 terabyte of RAM. Actually, there are servers today, we have 1 terabyte or more of RAM. And if you think about what you can store in 1 terabyte, it's pretty interesting. You can store 1 billion of records, 1 kilobyte each record. Pretty good, right? So and finally, the memory density still grows with the Moore's law. And furthermore, there are all these new technologies like RAM SSD hybrid, which will just give you a lot of more memory, making it look like a memory because it's backed by SSDs. That's why you have more of it. It will be pretty cheap and very energy efficient. Okay? So that's one important trend. Putting data in memory, we are really using it aggressively. The second one, to support this interactive and streaming computation, so how can you reduce the duration of a job? One way to reduce it, to parallelize it, right? Increase parallelism. So here is another example, a simple example. Say you have this now, 2 maps, and this is a reduce, and you get a result. The maps reads from the disk, and this is how long it takes, capital T. If I can execute the same job on 4 nodes, so I have now 4 map tasks instead of 2, I am going to be, and if I can partition correspondingly the data, I can be much faster. Right? However, this comes with quite a few challenges because as you reduce how long it takes a task, now you are going to hit other bottlenecks like the scheduling overhead. So we have quite a bit of research of reducing the latency for parallel schedulers while achieving still high locality. Then the communication becomes a bottleneck. So we have some work to optimize parallel communication patterns. And finally, if you have a job which runs 10 hours and a node fails, you have some time to recover. If it runs, if your job runs in less than 1 second, if you have a failure, now you have a problem, right? You have to recover very fast. So all these challenges, we address some of them, and I'm not going to go into details, but I just want also to put in perspective what are the challenges when you try to provide interactive computations. And finally, we have techniques to trade between the result accuracy and the response time. So basically, this is what it says. It's like, I'm going to give you a result with 0.1% error, but I'm going to give you 10 times or 100 times faster. That's what's value proposition. And why you want to do that? Well, you want to do that. I told you that we aggressively want to use a memory. But it turns out that's not enough. If you look at the same numbers I gave you in the previous 2 slides ago, say you have a machine which, say, up to 512 gigabytes of RAM, and the I/O bandwidth is between the I/O bandwidth between the memory and the CPU is between 40 and 60 gigabytes per second. If you do the math, even if the data is in memory, just to scan it, you don't do anything, just scan it. It may take 10 seconds, right? Assuming no locks, no nothing. So when you are talking about interactiveness, which means response time less than 1 second, this is not, so just getting the data in memory is not enough, right? And the worst thing is that with other storage devices, this gap between the capacity of the storage and the I/O to access that storage is increasing. So this will become a bigger and a bigger problem. So here, the idea is you are going to smartly compute and pick samples for your computation, do on samples, and then come up with error bounds for those computations, right? That's what it is. So this is just saying that, it's in real life, it's like you have a trade-off between accuracy and also the cost, right? The scale today, the weight scales, you take your weight, right? You measure your weight. The best one on the market today, for consumer market, they have inaccuracy of half a pound. The speedometer in your car, do you know what is the inaccuracy? Up to 2.5%. It was this Edmundson study, 70 cars. This is what it is. And depends on the weather, tire wear, load of the car, all of this stuff. Right? So we are operating with this information. Today, most of the devices we are operating with, they do have this error built in. Okay, so that's another approach we have. To easily combine batch streaming and interactive computation, which is one other goal, we provide a single execution model to support all of them. So if we have an execution model, we support all of them, it's easier to combine. Then you have 3 execution models, 3 execution frameworks, each of them supporting one of these batch streaming or interactive models. To easily develop sophisticated algorithms, we provide powerful Python and Scala shells. And we also now start to provide high-level abstractions for graph-based and machine learning algorithms. And finally, we try to be compatible with the existing open source ecosystem. And to do that, we try to interoperate with existing storage and input formats like HDFS, Hive Metastores, Flume, and support existing execution models such as Hive and GraphLab. Okay, so that was basically giving you an overview of our approach. So now I am going to switch gears and really talk about the stack and give you an overview of the stack. So this is a stack of today's open source analytic systems. And the way we are different from it is in 2 ways. There are 2 ways we are different from it. First of all, we have this new layer which is called we call it resource management layer. And this basically allows multiple frameworks to share the same infrastructure. Then we add significant functionality in the other layer. Storage layer becomes data management layer. Now it allows to different cluster computing frameworks to efficiently share data. And the data processing layer, we develop new cluster computing frameworks which use in-memory processing, trade between time, quality, and cost, basically implement some of the approaches I talked earlier. At the application layer, we have some interesting application. Genomics, this is cancer genomics application. And Carrot, this is an application for mobile devices trying to identify which application consume a disproportionate amount of the battery. Right? So you can kill them if you want to lengthen your battery life. And the reason we do that, we look at the application, is to make sure that we drive the design and the development of the lower layers, having, real application rather than what we believe the application could be. So in the rest of the talk, I'm going only to focus on these middle three layers: resource management, data management, and data processing layers. All of this work is done in the AM Lab. So the AM Lab was launched in January 2011. It's a 6-year plan. It's going to end in 2017. Consists of 8 computer science faculty, around 40 students, and we also have 3 software engineers. It's organized for collaboration. These are some images from meetups. We have 2 retreats every year of 3 days. We meet with our sponsors and so forth. This is the floor plan of the AM Lab. The AM Lab is just in the building across the street, Soda Hall. And the main point we want to make here is that the faculty, we sit here. So this is open floor. We don't have offices. So we sit together with everyone. Okay, it's founded by DARPA and NSF through multi-million grants, but we are but also we have a host of industrial sponsors. 3 founding sponsors: Amazon, Google, and SAP, and 18 other sponsors, including Microsoft, Cisco, Intel, Samsung, and so forth. And the main goal of this lab is to build this Berkeley data analytics stack, which is the next generation of open source analytics stack for industry and academia. This is what we want to be. Okay, so now let's talk about all these layers. Okay, so now I just overimpose on these layers the existing stack. So it's again data management layer, you have the Hadoop distributed file system. The data processing layer, you have all these frameworks, cluster computing frameworks. Hadoop, on top of Hadoop, you can run Hive, Pig, HBase, Storm, which is for streaming processing, MPI, and so forth. Okay? So before going, so now I'm going to start from the resource management layer and go a little bit up. So our instantiation at the resource management layer is called Mesos. And Mesos is one of our most mature components. We started the development in 2009. And the most impressive things we can say about it is that it's in production on Twitter for more than 1 year now. It manages over 6,000 servers, and they run over 30% of their production services on top of these servers, on top of Mesos. So what does Mesos try to achieve? Well, look at what is the situation today. So today, say you have 2 cluster computing frameworks, Hadoop and MPI, and you want to run them. They are pretty different. So today what you typically do, you statically configure 2 clusters, one for MPI and one for Hadoop. Now the problem here, if the MPI cluster doesn't have anything to process, Hadoop cannot take advantage of these resources. You lose these resources, although maybe Hadoop has a lot of backlogged jobs to do. Okay, so you lose the opportunity for this statistical multiplexing. The other thing, remember, here we are talking about big data. Okay? So big data, and in many of these cases, the Hadoop and MPI, you want to share the same data. Okay? And if you have two clusters, what do you do about data? You replicate it, it's pretty expensive. You access remotely, it's pretty expensive from the point of view of performance. Okay? And finally, it's hard to cooperate. You know, if you want to write an application or a pipeline which uses Hadoop to preprocess some data and MPI to implement some linear algebra optimization on the data, you know, how do you do it? It's hard. So basically what Mesos allows you is to run multiple frameworks on the same cluster. Right? So instead of having two separate clusters which runs Hadoop and MPI, you have one cluster which runs Hadoop and MPI on top of Mesos. Okay, so it's like multi-programming for data centers. Okay, that's what it is. So Mesos is a common resource sharing layer which abstracts away or virtualizes resources to frameworks. And of course also enable diverse frameworks to share clusters and also provide isolation between frameworks and all of this stuff. So here just to give a sense what Mesos achieves. So here like are 100 nodes. On the x axis we have the time, and we have 4 cluster computing framework instances. We have Spark. I'm going to talk a little bit about it. It's our cluster computing framework. 2 Hadoop instances and 1 MPI instance. And we have 100 nodes. One way to do it, you divide it, say the policy is that each of them should get the same number of machines. So you have 25 to Spark, 25 to each of these Hadoop instances, and then another 25 to MPI. Right? That's one. Now, if you run them on top of Mesos, this is what will happen, at least in this example. So on the y-axis is that what is the percentage of the nodes which is used by each framework. Okay, so here are some interesting cases. So at time, I don't know, a little bit over 300 seconds, you see there are only 2 frameworks which are active. One is the MPI, and this is using only like around 15% of the nodes. The other one, the large Hadoop mix framework, take advantage that no one else is using the resources. It expands and uses all the available resources. Right? If we wouldn't have used this and we do statical partitioning, the large Hadoop mix will use only 25 nodes, and you have more than 50 nodes unused. Now here, all of them are active. So each of them get more or less 25% of the resources. And finally here, this Facebook Hadoop mix becomes active. So the main point we want to illustrate here is that, you know, it's pretty fast. The Facebook Hadoop mix, it gets the resources it deserves, right? It's entitled to. Okay, so this is again seconds on the x-axis. So that was Mesos. Now let me skip the data management layer, and I'm going to talk a little bit more here about the data processing layer. So Spark, it's a cluster computing framework. It's the first one we build. And actually we build it to demonstrate that it's much easier to build new cluster computing frameworks on top of Mesos. In the meantime, Spark becomes, you know, one of our most, if not the most popular component. Okay, so when we build Spark, we really wanted, we have, it's in the AMP lab, we also have machine learning people. And they are trying to implement these machine learning algorithms on top of Hadoop. And it was slow. Why it was slow? Because each iteration of these machine learning algorithms are iterative. And each iteration was implemented as a MapReduce job. Okay? So this means that between iterations, you have to write and read from the disk. Because that's how the MapReduce jobs exchange the information. That's very slow. And then we also want another category of workload we want to support is interactive computation. So what we did, Okay, we say we put the data in memory. But then the key question is the following. As long as we want to increase parallelism, put data in memory, what happens when the node fails? You lose data, right? So what do you do in that case? So in order to address that problem, we build these resilient distributed data sets, or RDDs, which are fault tolerance in memory storage abstractions. Now, how do you provide resilience if you have the data in memory? How does HDFS on disk provide resilience? You replicate, right? They have three replicas or whatever number is configurable. So you can do the same thing in memory. You replicate. The problem with that is that memory is still expensive. So now you are going to have 2 copies sitting in the memory. More than that, it will also hit your performance, because now you need to use a network. You are going to be limited by the network I/O, right? Because you need to create the replica. Okay, so we didn't do that. So instead, what we do is that these resilient distributed data sets, they are immutable and can be created only through deterministic operation or transformation from other RDDs. And then for each of these RDD in its handle, we have what we call is lineage. So lineage means a sequence of operation which are applied to create that RDD. And now you have a failure, you reapply the sequence of operation and you recreate the data. So here is a simple example. So say you have a 2-partition RDD A, this is stored on the disk. Then you have a transformation F, a filter, which loads RDD A and again filters it and store it in memory. It's RDD B, again 2 partitions. Then you have a shuffle here and another operation G, say this is a reduce operation, which creates an RDDC, and now you have an aggregation operator which takes this RDDC also and come up with the result, which is RDDD. So now assume that before H has a chance to get the input from partition, to get the partition C1, the node on which the partition C1 has failed. So what happens in this case? Well, Spark has, again, maintains with the partition C1 all this operation which are used to create C1. So in this case, it's going to just use that information to rerun this operation and recreate C1. So in this case, maybe you'll find another node and then executes G on B1 and B2 and recreates C1, then feeds it to H, and now you have D. Okay? Well, and it turns out that, as you may expect, it performs very well. So here is a comparison between Hadoop and Spark for 30 and 60 machines. And this is a number of iteration. This is a page rank algorithm. And these are 2 other simple machine learning algorithms, K clustering. So you have an improvement here, 40 times, close to 40 times. And for logistic regression, you have over 100 times. Why do you have different improvements? It turns out because you have different degrees of communication in these algorithms. So when the communication starts to dominate, the improvements will reduce. So, Spark, we have the Spark community today is quite vibrant. We have over 700 meetup members. Many companies use Spark today. And actually one of the things we are most proud about is that 17 companies actually have contributed back code. Actually in the last few months, the last 2 or 3 months, the lines of code contributed from outside Berkeley is significantly higher than the number of lines contributed from within Berkeley. Okay. So Spark was this one. So it provides support for batch and interactive applications. Now we have a new module which is called Spark Streaming. So now this adds the ability of Spark to also provide streaming functionality. Okay? So how we do that? Now, the existing streaming systems, this is the way they work, the high level. You have these long-running operators. You have a graph of these operators. And then records come into the system, and they flow through this graph of operators. When one operator gets one of this record, it updates some internal state, and then maybe generates one or more records for the next stage in this data flow graph. So what are the problems with this? Well, a few of them, but one of them is that what happens on failures. What happens on failures, you can, there are a few techniques. One technique is basically you replicate the computation. You do the same thing twice. The other one, before you process the data, you store it in some durable store. So if you fail, you can feed the data to another node and rebuild it. Okay? The problem is that it's a little bit it's complex, and it's often is slow. Okay? So this is challenging. So what do? We do something very simple. What we do, we run a streaming computation, a series of very small deterministic batch jobs. So now imagine that you can run a job, a MapReduce job if you wish, in less than 1 second. So one way to implement streaming in this case, you run that job every 1 second, and you update the results. Right? Okay? So this is what we do. The live data stream comes in, Spark streaming, chop it in batches, a few seconds or less than 1 second, and then feed the batches to Spark, which is doing its computation and updates the results for each batch. Okay? So that's what it is. So what are the advantages? Well, the advantage now, you transform the streaming computation into a batch computation. And with a batch computation, we know how to deal with the failures, we know how to deal with the stragglers, and all of this stuff. So you reduce the problem of something you know. The other thing is now, we have Spark also can do streaming. So Spark now can do streaming, interactive processing, and batch processing. Okay? What do you lose? Well, now the latency is dictated by these batch sizes. So, the latency here, the batches we are using is 1 second, maybe half a second, 2 seconds. So if that's good for you, we believe this is a great model. If you want millisecond delays, latencies, or microsecond latencies, like in banking, this is not a good solution. Performance-wise, it scaled very well. These are some simple benchmarks, grep and word count. On the x-axis, the number of nodes in the cluster. On the y-axis is throughput. And this basically says that it scales well. One line is for 1 second batch sizes. The second line, the blue one, is 2 seconds. So you have a larger batch sizes, you have a better throughput. Because there is a fixed overhead you pay with this batch. Okay? So this is just showing linear scaling. Comparison with Storm, which is a streaming system today, in use today, most popular today. We are significantly better in terms of throughput. Green is Spark, red is Storm. We also show that we are not sensitive to the record sizes. Why? Because we are only sensitive to the batch sizes. Right? If you have here smaller records, we feed more in a batch. However, the Storm is sensitive to the record size. Why? Because with processing each record, there is also a fixed overhead you need to pay. And this is, for the both application, you have the plots here, grep and word count. These are like a few months ago. And when I started to motivate this approach, I say, well, the current systems, streaming system, or the existing approaches do not handle well failures. How do we do about the failure? Well, it turns out that we do very well. So this is the latency. These are the iterations. And this is latency of one each iteration. So it's 1.5 seconds in this case. We run it on 10 nodes, and here at times 30 seconds, we have a failure. Right? One node fails. So you see, it recovers from the failure, and you have a blip here. It's of 0.6 seconds, but then you recover pretty fast. Right? And it's again, you don't pay a big penalty. So why is this happening? Well, what happens is that when the node is failed, there are many of these RDDs, many data, a lot of these small pieces of data are lost. When you recover it, you don't need to recover, and the system doesn't recover all this data on one machine. It can spread the recovery. It can do the recovery in parallel. If the two data pieces are not dependent, they can be recovered in parallel. So that's how you have very fast. Right? The current streaming systems, which don't do full replication and just store the input data on a resilient store, then if a node fails, you need to feed the entire all the records to reveal the state on only one node. Okay, so that's a big advantage. So that was Spark streaming. The next one is Shark. So the Shark component provides SQL interface on top of Spark. More precisely, it runs Hive, which provides SQL interface in the Hadoop world over Spark engine. So instead of having Hive over Hadoop, you have Hive over Spark. This is Shark. There are some more changes, but that's the main idea. So this means that we are compatible with Hive. So any query you run on Hive, you can run on Shark. But it will be much faster. And it's again, we have here adopters as well. The most impressive one is Yahoo. They are running on hundreds of nodes. Okay, so here are some results. So this is Conviva. It's a video company which provides video management for some premium content brands like HBO, MLB, ESPN, and so forth. And this is just to show how we perform for some realistic workload. These are query 1, 2, 3, 4 are the top 4 queries in the workload at Conviva. And we have 3 lines here. Hive, this is a SQL over Hadoop. Shark, the green one, Shark disk, which when the data is on the disk. And blue when the data is in memory. Okay, so when the data is in memory, you would expect significant improvement. And indeed you have. When the data is in memory, a query when you run on Shark, it takes 2 orders of magnitude less than in the case of Hive, when the query is on the disk. Right. Now, the interesting aspect is that even when the data is on the disk, Shark takes much less than Hive. Why? Because of host of improvements we have. We use a column-oriented storage instead of row-oriented storage, which is much more efficient. We also have many other improvements, like scheduling. With Hadoop, it takes you between 1 and 3 seconds to just learn that a slot is available to schedule a new task on it. This is much better. In case of Spark, it's milliseconds. We also improve the communication pattern like a shuffle. It's like shuffle as compared with Hadoop. Okay? Yeah, and we are pretty happy about that. This, you don't need, if you want to try it, you do not need to install on your cluster. If you wish, you can go to Amazon. They provide you the scripts, and you can run that both Spark and Shark on Elastic MapReduce. And actually, they updated the script, so it should be even better now. Okay. The next component, I'm going to go to this data management layer, is called Tachyon. So the Tachyon, I told you a little bit about this RDDs, this abstractions, storage abstraction for memory. Right now that abstraction sits within Spark. So if you have multiple Spark instances which operates on the same data, each of the instance will take that data and store it in memory. So you have duplication there. So Tachyon, it takes these RDDs out of Spark and provides a storage abstraction like a service which can be used and can be shared between different cluster computing frameworks. It's like on your computer, the ability to have shared memory, which can be shared by many applications. Right? That's what it gives you. Tachyon also has HDFS, it provides HDFS API, so you can actually run Hadoop on top of Tachyon. It will be faster. Okay? BlinkDB. BlinkDB is this system which allows you, if you remember at the beginning, I told you that one of the approaches we are taking to improve the interactiveness is to allow the user to trade between the error bounds and the response time. So this is what BlinkDB allows you to say, okay, I want this result to give me the fastest result as long as the error is less than 0.1%. Okay? Or give me these results in 2 seconds and also tell me what is the error. So here it's, I think this is the last evaluation I have. So this is shows BlinkDB versus Hive and Shark. So there are 2 data sets, 2.5 terabytes and 7.5 terabytes. They run on 100 machines in both experiments in Amazon. And the 2.5 terabytes is small enough so it fits in the memory of the machines. The 7.5 terabytes is large enough so it doesn't fit in the memory of the machines. So red is Hive. And on the y-axis, you have the query response time. It's a simple query in this case. And as you can see, and again, notice that the y-axis is log scale. So for the 2.5 terabytes data set, it takes 2,000 seconds. For the 7.5 terabytes data set, it takes, maybe 4,000 seconds. So it's pretty a lot. Now, let's say you use Shark. So Shark with 2.5 terabits, everything fits in memory. It takes only now 100 seconds. This case uses the old version of Spark, which didn't get a lot of improvements versus Hive. So the reason you have pretty close here is that both of them, they use data from the disk. Now we run BlinkDB with a 1% relative error and 95% confidence interval. And what you get that for 2.5 terabytes data set, it takes 8 seconds. So 12 times better than in the case of Shark, when it operates on the entire data set. And for the 7.5 terabytes data set, it takes 10 seconds. So it's all the way 230, 300 times faster. Right? So if you can accommodate 1% error, you get 2 orders of magnitude the response faster. Okay? So finally, 2 other components I'm going to present briefly. Spark graph. So this is a component which implements the graph computations on top of Spark and provides GraphLab API. GraphLab is a popular graph computation engine which was developed at Carnegie Mellon. And we also have a machine learning component, ML-based. And the goal here is to make machine learning accessible to non-experts and make it easier for experts to add new algorithms. Everything which is dark blue, we have released. It's in use in industry. The light blue are things which are planning to release or are in development. However, Tachyon, we do have a developer release, and Spark Graph and BlinkDB, there we are going to have the first releases June, July timeframe. ML-based, it might take a little bit longer, although we still hope to have a very basic release this summer. So finally, the last, if you remember, the last of our goals is to be as much as possible compatible with the open source ecosystem. Because why? Because, you know, if you have your Hadoop cluster, we don't want to ask you, throw it away and use our stack, right? We say, okay, use it side by side, and you'll see, at least for certain application, you'll see certain, you know, great benefits. So how I try to address this to achieve compatibility goal? First, we support existing interfaces whenever possible. For instance, like I mentioned, Shark provides a Hive interface. You can run Hive queries on top of Shark. Tachyon provides HDFS API. You can run Hadoop on top of it. And here we provide some compatibility layers for Hadoop, Storm, and PI, so you can run without changes on top of Mesos. Finally, for Spark Graph provides a GraphLab API. The other way we provide compatibility with the existing OpenStack is use existing interfaces whenever possible. For instance, Spark supports HDFS API, S3 storage API, Hive metastores, and so forth. BlinkDB supports Hive API, so actually you can run on top of Hive. And this is something that Facebook is doing. And finally, Spark Streaming ingests many of these inputs, formats from Kafka, Flume, Twitter, or raw TCP sockets. So, in summary, what we do in this lab and with the Berkeley Data Analytics Stack is we have a holistic approach to address the next generation of big data challenges. In particular, we support interactive and streaming computation by using in-memory, fault-tolerant storage abstraction, low-latency scheduling, and so forth. We make it easy to combine batch streaming and interactive computations, and we do that by providing one execution engine which can support all of them, Spark. We make it easy for the developer, or easier for developer to write sophisticated applications by providing Scala interface APIs for Java and Python. And I didn't tell you, but in general, the Spark model is much simpler than the Hadoop MapReduce model. Typically, you need between 5 and 10 times smaller, fewer lines of code to do the same thing. So it's not only faster, but it's also more flexible in general. And like I said, it's we try to be as much as possible compatible with the existing open source ecosystem. Everything is, it's what we built. It's open source. There are no IPs. And we are fully committed to release high-quality software. That's why end of the last year, we starting building a 3-person software engineering team, which is led by Matt Massey. And Matt Massey, if you heard about Ganglia or use Ganglia, he's a creator of Ganglia. And he was also one of the first engineers at Cloudera. So we try not only, to build a software engineering team, but a high-quality software engineering team. So thanks. If you have any questions, I'll be happy to answer. Yes?
Can you go back to that slide where you do that?
Like this? Okay. Can you go back to the slide where you show the load balancing for Mesos, like with all those colored pictures?
Is this a good one, or?
The colored one, where you have 4 kinds of loads.
Oh, 4 kinds of loads. Yeah, sorry. Yeah, sure.
Yeah, this one. So basically, what you show is sort of like a win-win situation. So, but apparently there are some. Okay, it's going to show up.
Yes, go with the question.
Yeah, so
Yes.
I'm just thinking about some kind of drawbacks of having it on one cluster, right? So apparently, say where they all take like quarter of resources. I'm just curious if they sacrifice any response time. Or, for example, if you have only two of them, most probably everything would run faster,
Yes,
right?
No,
so it's a trade-off here.
There is excellent question. So basically, what are the downsides? I only painted the rosy picture. Yes, I think that there are two types of challenges and maybe drawbacks. So one, you need to be very careful to provide isolation between the workloads, right? So we try to do that. The other one, it says, well, okay, I am not using the cluster, but if I have my dedicated cluster and I want to use it, I get everything right away. What happens in this case, right? It's not right away. It's a little bit of a slope here, right? It's not an infinite one. Because I need to wait for others to release the resources in order for me to use, right? So that's a very good point, and again, depends on the application and what you want to accomplish. We do have also the ability to preempt, right? And for instance, for Hadoop, you can preempt it. In the worst case, you execute the task. So if you really want to have a very important real-time job, you want to get the resources right away, you preempt the resources from the others. Mm-hmm. However, you need to be careful here, right? Because with Hadoop, you can preempt, it's working. But MPI, you cannot. If you kill an MPI task, you say goodbye to the job. You need to rerun the job. So actually, that's why if you see, the MPI doesn't exceed 25%. So it's never preempted. So you are going to pay that penalty there. What is this saying? Is that if you are a cluster and you have a workload, right, you can be preempted. You can give the resources you have back without big penalty. Then you are going to greatly gain from this one, from the statistical multiplexing, because you are going to be very opportunistic to use any free resources. Because giving it back doesn't incur you a big penalty. For the MPI, you need to be much more careful. Maybe MPI doesn't benefit as much.
Do you have any cost model behind it which you use?
We don't have a cost model necessarily. We have a pluggable module in which you can define your own policy about how much each of these frameworks is going to do. And you can define, max share if you know what a framework capabilities are. So you can specify that, MPI, even if everything is available, you shouldn't get more than 25% of the resources.
May I ask another brief question? No?
Yeah, I think we have time.
Yeah. So, by the way, I'm Vladimir Zadorov from University of Pittsburgh, Pennsylvania. Pittsburgh from far away. So, if you can go to the lineage, like you say, you can use lineage to recover those data sets. Is it always possible to do that? For example, if some of those operations, I don't know, for example, random sampling, you won't be able to recover identical C1 from B1.
You have to have the same seed. If you do sampling, you need to have the same seed. You need to have the same seed. The assumption here, and in most cases this is accurate, these are deterministic operations.
Mm-hmm. Okay, so in principle, I can probably invent more operations where you can do it for certain kind of operations under some constraints.
Yes, but it turns out even in your case, actually, that was a very good point. What happens if you want to do random sampling? It turns out that you talk with the users. Actually, they want to have the ability to deterministically get the same sample when they have, for instance, debugging and things like that. So within the same job, right, if they execute it, they want to get basically the ability to be deterministic. Mm-hmm. Because if you have a bug and every time you get a new sample, it's a problem. Mm-hmm. So I think that from our experience, yes, there are cases in which this will not work. But the vast majority of cases will work. But even, MapReduce. The MapReduce is doing something very similar, although not this scale. That's the way you recover from failures. You execute the task. Yeah. And by the way, we do check. We have a fingerprint. We have a checksum on the RDD we recompute. So we can at least know if we are not We didn't compute the same RDD.
But you don't do any post-processing, like verification whether the
No, we do
recovery
the
is-
verification is what I'm saying. We have a checkpoint. Right, with all the lineage, you also have, not checkpoint, checksum.
Mm-hmm. Okay, thank you.
So could you talk a little bit about, in the case of BlinkDB, in order to provide error estimates and confidence intervals, you have to make some assumptions about the distribution of the data. And in general, you're going to be looking at data with very weird statistical properties. Do you learn those distributions? Do you assume them? Do you give the user the ability to model that? I mean, it's a tough problem.
It is a tough problem. It is a hard problem, yes. So, this is active area of research. And so here is the approach you are taking. And, the way you compute the errors, it depends on the distribution, it depends on the sample size, it depends on the operation, right? And there are operations like aggregate operators for which you are going to have closed formulas, there are others you don't have. So what we do, we use this bootstrap in order to evaluate error, right? Which is this kind of big hammer, right, you have. And this is supposed to work on arbitrary function. Actually, it's not that. It works under, like everything, works under certain assumptions. Like the function, your function is what is called Hadamard differentiable. So, and actually, it's, even if it's very hard to, if I give you a piece of code to see whether that's Hadamard differentiable. And that's also, it's a sufficient condition, it's not a necessary condition. Which means there are some functions which are not Hadamard differentiable for which bootstrap can work. So what we do and the approach you are taking there, we develop diagnosis. Okay? So we develop a diagnosis and basically say, I get an error. Is the error good? Right? And that's also is not infallible, but we get pretty good results so far. But that's the idea. Basically, you apply your techniques to compute the error, and then you have a diagnosis. Did the technique work or not? And you apply this technique on that query, on that distribution. That's a very good question.
So I have a couple questions about the GraphLab-based API. So
about what?
GraphLab API.
GraphLab API. Yeah.
Okay.
Yes. I don't have too much about it.
So first question is, so for current GraphLab is mostly the in-memory static graph analysis, right? So actually we talked with like Joseph and some other folks from GraphLab. Do you plan to support the graph builder stuff, just to take the data from HDFS or
yes.
from?
Yes.
So is that going to be part of the GraphLab?
Yes, actually one of the reasons, yes. You see, so I still can show something interesting here then. Yes. So the reason we want to develop this, and actually we have a version, and I suppose not only GraphLab API, also Pregel kind of API now. We run on top of Spark for two reasons. One, Spark has access to HDFS, knows how to write HDFS. The other one is for resilience, right? Because it runs on top of Spark, you have the resilience for free. So yes, you can, HDFS, everything, it's access to it. The disadvantage, at least for now, this is in Java. So, it's slower than GraphLab. We are still optimizing it, but I think we are, from talking with people, we think that it's the right trade-off. There are, talk with people basically saying, if it's Java, I very much prefer Java, even if it's a little bit slower.
Yeah, then in terms of the graph database, where do you want to save the graph data?
We can save, it again depends. If you can save in Tachyon or you can save on HDFS.
Okay, so it's not decided yet, right?
No, but HDFS, Tachyon provides HDFS API. Think about in a super trivializing things, Tachyon will be like a cache, like a caching, a persistent caching, right? So if you want your output to be used by another framework or by someone else, and you want to share, maybe you prefer to share through memory. If you want just to store it for a future retrieval and so forth, you store it on HDFS. But in all this stack, for now, the only one which uses a file system and so forth is Spark, and Tachyon, which is a caching layer. Right? Okay. And Spark is again supports HDFS, S3, Hive metastores.
Okay, thank you.
Yeah. So I probably misunderstand something about the technology, but it sounds to me like Spark is essentially moving to RAM where there would have previously been the intermediate state saved to a disk, and then you have another layer of resiliency on that. If we were using Hadoop, though, it'd already be fault tolerant. We'd already be allowing for systems to fail, and so your resilience layer as well as the development of the system both have costs, the overhead cost of the resilience layer. Do you have any comparisons of Spark to running Hadoop from just a RAM disk, making it think it's a hard disk, and seeing what the additional development has actually provided here?
Yes. If you run, let me put it this way, if you run Hadoop on the RAM disk, you'll have an improvement several times. If you run Spark, you have 100 times. Why is that? Because if you run on RAMFS, you are still going to use Hadoop to pay the deserialization cost. With Spark, you can keep the data in deserialized form. Also with Spark, and especially with Hive, you can give data, and you are keeping the data when you do Shark in column-oriented storage. And column-oriented storage is just you need both less data from the disk. But the other big advantage is deserialization. Because deserialization, if you do one row at a time, a row can be a complex structure, many fields. That's expensive. If you do deserialization of the columns, you have an array of primitive data types. That is very fast, even for Java. It can be also all at memory speed. The other thing what I mentioned to you is that the scheduler overhead. The scheduler overhead in Hadoop is pretty high. It was designed for a different workload. In our case, it's milliseconds. There is seconds. Right?
Yeah, it sounds like you have great points. It's just I'm still not hearing a number for Hadoop versus the 100 times on Spark, and it seems that those numbers should be in one of your graphs.
Okay, yeah. Depends on the workload. Yeah. We have that. I have to retrieve that graph. You should look into the Spark paper. In the Spark paper, as far as I remember, we do have Hadoop running from RAMFS. But I'm telling you, it's the serialization and the deserialization bottlenecks in Hadoop. Just you can use that number.
The take-home message of this,
excuse me?
The take-home message of this talk, based on what I understand, up to this point, is that Spark is good. Use Spark if the data for your job fits into the memory of the system. So, are there other considerations to have in mind when you're deciding between Hadoop and Spark?
So many of our users, actually, they like the programming model. They say even without the advantage of the performance, they prefer Spark once you start. Because Spark is more flexible. Its model is similar with SIMD. You have a sequential program, you write a sequential program, and you have these RDDs, which only the operation happen in parallel. Right? It's much more flexible than MapReduce. That's one. The other thing I just want to remind everyone. So here I am comparing, it's Hive, not Spark, and Shark. But Shark is over Spark. And here you have improvements, significant improvements, even when the data is on the disk, because some of the reasons I just mentioned earlier, right? And the other one is about this BlinkDB. You can be so much faster, right? And there, with the samples, you have majority of samples fit in memory. We are going to talk about, fit in memory on one machine, samples, hundreds of million data points.
Thank you.
We have time for about one more question.
Could you elaborate a little bit on what the Python interfaces look like? And you mentioned them a couple of times, but if you have any details for a minute.
Yeah, I don't have any details on that. So the Python, so basically it's again, you write a Python program and you have the RDDs. And for RDD, you are going to use a closure. This is what, to have an elegant way. So then basically what happens is so I didn't show how the Spark is working actually. You have a master and a set of slaves. The master runs the program. Now these RDDs, which are these partition parallel data structures, are going to be shipped, and they are on the slaves. And then you ship the code, and then it's executed on each of these of the slaves, and the result may be aggregated back. But everything happens under the hood. Yes. So basically you ship that transformation, which is a Python code, goes to the slave and work on the partition. Okay, any other questions?
Well, if there's no more questions.
Thank you.